Thank you everybody for being present. So my name is Stefan Pichmal, and I will present a joint work with Florence Nicole. We are both from the French Civil Aviation School. So the work here is dedicated to finding possible candidates for densities on surfaces that will behave roughly as von Mises distributions. So just to begin with, but in fact, due to the numerous presentations before involving directional statistics, you will not be surprised by the form. So a von Mises distribution is a rotation invariant distribution defined on the sphere. And in fact, the expression is given by the complicated formula here, the complication coming only from the normalization vector, because the exponential part is very simple. It is just the inner product between a given centroid, mu, and a point on the sphere. So here, the important properties are that first, the von Mises distribution is a good approximation to some other rotation invariant distribution, namely something that is known as the RAP normal distribution. That turns out to be also the heat kernel on the sphere. So there are many uses in practice of directional densities, mainly to estimate density. They will serve as kernels to estimate the densities. We can try to extend the notion of directional densities to other kind of spaces other than the sphere. So a very classical example is the torus, and if you work the same procedure on the torus, you will end up with something that is quite easy to deal with, because the expression is very similar to the sphere case, with something that is slightly different, that is coming from the second part, that in fact is not necessary. And if you keep only the first one, what is really interesting is that you see that everything depends on angular coordinates, namely differences between angular coordinates of the point of interest, where you want to evaluate the density, and the centroid. We can also try to go to things where the definition is not so obvious. So here we are moving to the hyperbolic space, and here there is no, say, unique way of defining von Mises-like probability density. So you can try to extend the standard definition, but you also can try to use a property of the von Mises distribution, the standard one, that is, in fact, it is the exit measure, the exit density of a Brownian motion started at the origin of a disk and with a drift. And in fact, if you have no drift, you will end up with harmonic measure, but if you have a drift, you will end up with von Mises density. So if you work this approach for the hyperbolic space and you want to find an exit density, then you can have an equivalent definition of the von Mises density, but for the hyperbolic space. And you see that in such a case, it is much more intricate. But anyway, what we see is that, of course, we depend on the distance to the origin, because it is an exit probability. But also we have something depending on an angular parameter. Okay, once again, we end up with angular parameter. So the question is it possible to proceed the same way for more general surfaces? So we have seen torus, spheres, here, in fact, circles in the hyperbolic plane. Is it possible to extend to something more general? So here, to be honest, I will not give you a general recipe that will allow you to have von Mises densities on everything. So I will just do something more simple, that is the case of surfaces. So for a surface, we may try to use something that is related to exit densities, but in such a case, you need to be able to represent the surface as the boundary of something. Okay? So it is quite difficult to do that, but say, at least on a heuristic level, you can imagine that you will end up with something that is very similar to the heat kernel on the surface. And in fact, it is what you have on the circle. You remember, von Mises density are close to approximation to the heat kernel, the wrapped normal density on the circle. So this is the idea we will use to obtain something that will behave like von Mises density. So first of all, there is a quite easy to obtain expression of the heat kernel on the hyperbolic space. So the expression is complicated, but in fact, it is an integral transform known as an Abel transform. So it is very easy to obtain the heat kernel from the Abel transform of the standard heat kernel in R square. So the expression is here, and if you consider a general surface, so I will show you how to do that right now, we can start with the heat kernel on the hyperbolic space, and in fact wrap the heat kernel to obtain the heat kernel on a surface. So what is the idea behind? I will use the board. Okay, so imagine you want to represent the torus. Okay, so the torus has a nice property, two-dimensional. It has very nice property because it admits a flat model. So what is the idea behind? You start with a strip of paper, okay, and then you will glue opposite points. Okay, so it worked, of course. You will end up with a topological model of the torus, but you have more. If you look at the points here, of course, they will be identified by the process, and there is some magic here. That is, if you sum the angles, you end up with 2 pi. So it means that it is possible with a flat model. Okay? Now imagine you go with something that is more complicated. I'm not sure to have the right number of, it's also important. And I want to do pairwise identification to obtain a surface. If I do that, I cannot do that with a flat model, because if I sum the angles, it will not work. Okay? So to have something that is tractable, you need to in fact use an hyperbolic model. That is, you will have angles looking like this, etc., etc. And in fact, in such a case, you see that if you identify, you may end up with something that is sum ups to the right side, the right angle. So it means that we will, in the presentation, be dealing with surfaces that can be obtained that way. Meaning that we start with an n-gon in the hyperbolic plane, we use pairwise identification, and we end up with an hyperbolic model of the surface. In such a case, it's quite easy to see that we can obtain the heat kernel using wrapping, as in the second case. The problem is, of course, that it's uncomputable, and we will see how to deal with the problem. So, we can simplify the problem. That is, instead of summing right on all the elements of the group of hyperbolic isometries, we can separate the summation using primitive elements. That is, primitive elements are elements that are not, in fact, the power of another element, and split the sum into a sum over the powers of the primitive elements, and then over the elements of the conjugacy classes. And so you end up with something that seems more complicated, but in fact is much more tractable. Looking just at the final term, you see that what is really interesting is the wrap kernel along a primitive element, and in fact any primitive element is conjugate to a scaling, so finally the elementary kernels will look like a sum with just a scaling. And if we go back to the definition of the hyperbolic distance, if we consider elements located on the same y-axis, so it will not be exactly what we have here, but we will see that it will be an approximation. Then we can obtain the following result, that is, the kernel is periodic, of course, it's not very complicated. The L is the length. In fact, we can show that the primitive elements are related to minimal length closed curves, and in fact, the minimal length curve is the capital L. And so the kernel is periodic. We can compute its Fourier coefficients. So you have the expression here. And it's not interesting by itself, of course, you imagine. But what is interesting is that we have asymptotics. So, first of all, it can be shown quite easily. To compute the Fourier decomposition, you can keep only the first terms because they are decaying very fast. And second, in the limit of high concentration, so it is, in such a case it is small t, we have an asymptotics. So it is the same case as in the case of, remember, right normal distribution, we go back to the von Mises, it's exactly the same. And we will see that the asymptotics is something that is very, very similar to the von Mises distribution on the circle. Okay? The only difference between that, we have an hyperbolic cosine and a minus sign in front of the expression. But it is exactly the same. Okay? It's quite surprising, it's quite amazing. So now, if we want, I have time. 1 minute, 2 minutes. So now, you remember in a sum, we have something that involves, in fact, conjugacy classes. So we do not only need the elementary kernels, we need also to sum over conjugacy classes. And in fact, this is not really tractable. So in practice, we will try to do something that is an approximation. We will keep in the sum only the term that corresponds to the highest value. Okay? So if we do that, we will end up with a kernel that at the end is exactly the same as take the form that is here, the elementary kernel, and turn it into a multivariate distribution with all the L's becoming, in fact, the distances along the minimal closed line, and you will end up with something that is a candidate to be, in fact, a von Mises distribution on surfaces. So, first of all, the interest is that it is tractable, meaning that it is possible to compute. The problem is that right now it is just obtained by asymptotics, meaning that we have no idea about the underlying properties of the density. So the work that must be done right now is to investigate the properties of the distribution. Okay. So I think I have finished in time. Yes? Yes? Okay, thank you. So if you have questions.
Are there any questions? Don't be shy. No, I have just one remark if no one wants to ask a question. So I've come across a work of Barndorf-Nielsen where he defines a density which he calls the hyperboloid density. I'm sure you know that.
Yeah.
Yeah. And to explain to the audience, it's we look at the hyperboloid model of the hyperbolic space, and we actually define something just in the same way as the von Mises-Fisher density, but using the Lorentz metric of the ambient space instead of the Euclidean metric, and that works fairly similar to von Mises-Fisher. So I would like to ask you actually, what do you think of that thing as being a natural candidate for extension of von Mises-Fisher, and what is the difference to maybe what you have presented?
So in fact, the real question for being a candidate to a von Mises distribution on a general surface meaning that we do not limit to the, it's not, here the work presented is not dedicated to obtain a von Mises density on the hyperbolic plane. Okay, so it is really for a surface of genus larger than 1. So we want to obtain something as a quotient. Okay, so the question is how to obtain good asymptotics. So here the work starts with the idea that we want to obtain an asymptotic, but in fact the model we use in fact will dictate how easy is it to obtain the asymptotics. So in your case, in the case of the hyperboloid model of the hyperbolic plane, I don't know. Meaning that perhaps it's easier, I don't know.
Thank you. So, if there aren't any other questions, then let's ask the speaker. Thank the speaker again, please.